So today I'll be talking about the air quality in subways in the northeastern United States, namely on the composition and a little bit on toxicology of the PM 2.5. Uh, doesn't seem like I can change the slide. Can you move forward one? All right, thank you. So I don't think, can you go back one more? Okay, so I don't think that subways require introduction, but I would like to point out that subways are becoming ubiquitous around the world. There's over 180 systems in 178 cities around the world, and these numbers are only going to grow as cities and countries continue to develop around the world. Subways move a lot of people in a fast and efficient manner. 168 million people a day around the world, and a few million of these people are accounted for in New York and other subways in the Northeast. And subways are not only an important utility, but they benefit the environment. Moving a large number of people on the ground moves a large number of cars from the road, which has actually been shown to improve the ambient air quality in cities, including in China. However, subways are notorious for being dirty. The dirt and grime and rats are obvious in some systems, especially in New York City, but the air quality is not any better. Many studies around the world have demonstrated that PM 2.5 levels in subways is exceptionally high. Next slide. So what we focus on in our lab is the subways in northeastern United States, namely the PATH MTA systems in New York City and the subways in Philadelphia, Boston, Washington, D.C. Next slide. So this chart shows the PM 2.5 concentrations in these subways. I also included here the LIR, which is the Long Island Railroad. So the blue axis indicate the average PM 2.5 concentrations. And what is important to point out is that the PM 2.5 concentrations for all the subways are several times the average ambient value for all the cities, which is here on the left. The concentrations do, however, range widely. Philadelphia has average concentrations of 79 micrograms per cubic meter, whereas the PATH has average concentrations well above 600 micrograms per cubic meter, which is likely the worst in the world of any subway system. At one subway station on the PATH, Christopher Street, we've seen average concentrations above 1,000 micrograms per cubic meter. Next slide. So knowing the concentration is important, but it's not enough. PM with different compositions have different toxicology. And so determining the composition was a goal of the study. Knowing the composition of these particles can also tell us about their sources. So we collected PM on filters and analyzed them with X-ray fluorescence and absorption with a cyclotron. And we also wanted to conduct some preliminary in vitro toxicology tests. So we took that PM off those filters, extracted them, and threw them into lung epithelial cells, and we did oxidative stress analysis. Next slide. So this chart shows the overall composition of PM 2.5, a number of stations in 3 of the cities. So the first 2 stations here are from Boston, next 2 stations for the PATH in New York City, and the last 2, capital South Van Ness in Washington, D.C. So the y-axis shows the microgram element per milligram of total PM 2.5. These values are out of 1,000. You can think of them as a percent. In some cases, we overcounted, as in government center here on the left, where we got, maybe twice, we counted for twice the amount of mass that we collected. But in a lot of the other stations, we see that we actually have undercounted mass. But what's important here is that PM 2.5 is predominantly iron, which is here indicated in red, and carbon, which is indicated in black. And iron makes up for anywhere from 30 to over 50% of the PM 2.5. Other category, which is in blue, include a number of other heavy metals such as manganese, copper, and chromium. Next slide. So going further, knowing the elemental densities is sometimes not enough itself. You have different forms of each element with different mineral and oxidation states, can come up with different sources and have different toxicology. So we chose to look at the mineralogy of some elements. Here we see that there are many forms of iron present in the subway. About half the iron is hematite and magnetite. And what it tells us is that, well, these forms of iron are formed in high energy environments. if we try to think about where that hydrogen environment could be in the subway, it's likely from the friction as wheels grinding its rails and as the brakes grinding the wheels, or through electrical arcing with the third rail. And the other half, importantly, is ferrihydrite and goethite, which are formed under cool, wet environments over long periods of time. And we could think of this as rust, which tells us that a lot of the PM that's been generated there has been sitting there for a very long period of time. Next slide. So furthermore, if we look at these different look at the different oxidation states, we can determine what forms of iron are present in terms of their really the chemistry. So less than 20% of the iron is Fe2 plus, and Fe2 plus is considerably more soluble Fe3 than Fe3 plus, and also it produces what we generally consider more toxic radicals, such as the hydroxy radical you see here, compared to Fe3 plus, which produces only a per hydroxy radical. And less than 5% of the chromium on the subway is chromium-6, which is again considered a more toxic form of chromium. All in all, this is good, but it's also important to note that this aerosol is a complex mixture of many different metals and other components, which complicates the toxicology. But not only are different elements mixed in the same parcel area, but they could be actually found in the same particles, which makes it even more complex. Where we see iron, nickel, manganese, and chromium found on the same particle, whereas we see other elements such as copper being separate. Next slide. So to really understand the effects of exposure to the subway aerosol, toxicological tests have performed. We expose cal-3 London epithelials to 50 micrograms per milliliter, 9 cubic meter here, of the coarse and fine fractions of PM2 MTA stations in New York City, and measure the production of reactive noxious species. And we see there's a considerable amount of interstation variability, where we see there's a lot of stress for 2nd Avenue, but not for 14th Street, even though they're on the same line, on the F line. And we are attempting to replicate the results at the moment, and we're trying to expand our repertoire of tests to include common assay. Next slide. So in summary, we see that PM2.5 concentrations in subways are high, several times above ambient concentrations. The PM2.5 mass, PM iron and carbon, and those iron is a mix of rust and formed from high energy environments. The subway particles can potentially cause oxidative stress in lung cells. And just an important thing to say going forward is that we're actually conducting human exposure studies where we're putting volunteers on the subway for a period of 2 hours and measuring their cardiopulmonary function afterwards. We would like to eventually expand this to workers, but that is something we have to work on in the future. Thank you. Next slide. Questions?